to the section 9.1 video lecture, Estimating a Population Proportion. So what we're going to be talking about in chapter 9 is the idea of, if I get sample data and I have a mean or a proportion from that sample data, how do I find a range of values around that I'm pretty confident the population value falls in? So really good example of this that's really pertinent with primaries and things like that going on is the idea of this plus or minus. So like, for example, if you're reading polling data that says, Joe Biden is going to beat Bernie, it has 37% of the vote for the Illinois primary, plus or minus 4%. What that means is 37% is the estimate they got from their sample, and the range around it is what is where they think the population value falls based on their estimate and using probabilities. So that's what we're going to talk about in chapter 9. So a point estimate is the value of a statistic that estimates the value of the parameter. So this is your sample, proportion, or mean. That's what a point estimate is. It's a sample statistic that you get, a statistic that you get from a sample that you're going to use to estimate the value of the measure for the entire population. A confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. So it's an interval of values around a point estimate. The confidence level represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted as 1 minus alpha times 100%. So confidence interval estimates for a population proportion are of the form point estimate plus or minus the margin of error. Or they can be written as the point estimate minus, here, let me write this a little smaller. They can be written as the point estimate minus the margin of error, comma, the point estimate plus the margin of error. A 1 minus alpha times 100% confidence interval indicates that 1 minus alpha times 100% of all simple random samples of size n for the population whose parameter is unknown will result in an interval that contains the parameter. The value z sub alpha over 2 is called the critical value of the distribution. It represents the number of standard deviations from the number of standard deviations that a sample statistic can be from the parameter and still result in the interval that includes the parameter. So as your level of confidence increases, so like some pretty common ones are 90%, 95%, 99%. As your level of confidence increases, the area in the tails decrease. So there's less chance for missing out, because the tails are the part where you wouldn't get the parameter in your interval if it ended up in the tails. So if you're 90% confident, that means there's 10% of the area outside of that, which means there is 5% in each tail. So the area in each tail for 90% would be 0.5. For 95% would be 5% divided by 2, which is 2.5%, which is 0.25. And then for 99%, that's 1%, so that would be 0.005. So what we can do, the critical value is simply going to be something we did in the in previous chapters, which is normal distribution of, we're on z value, so 0, 1, and then we know the area in the tail, so we want to find the critical value. So we're going to use inverse CDF, and then we're going to input alpha over 2 into it, is where we get these critical values. So for the first one, we've got 0.05. So that's 1.645. For the second one, it's 0.025. So that's 1.960. And for the last one, it's 2.576. Okay, are the areas in the tails. So if we were doing this by hand, we would follow these directions, and then I'll talk about how to do this with the calculator as well. But things we know before, with the sampling distribution of p hat, so this is what we did in chapter 8. So for a simple random sample of size n, the sampling distribution of p hat is approximately normal, with mean equal to p and standard deviation equal to the square root of p times 1 minus p over n, provided that n times p hat times 1 minus p hat is greater than or equal to 10. Note, we are also required that each trial be independent when sampling from a finite populations. This means that the sample size needs to be no more than 5% of the population. In other words, lowercase n needs to be less than 0.05 times capital N. And the way you construct a confidence interval is you take your point estimate minus your critical value times the standard deviation of your interval, right? Because this z sub alpha is the number of standard deviations away from the mean we're allowed to fall, and then we multiply that by the size of our standard deviation in our example. And if we subtract it, that gives us the lower bound of our interval, and if we add it, that gives us the upper bound. So most of the time, we're going to do this not by hand. We're going to use our calculator to do it, and what it's going to do is it's going to give us answers that look like this. They're going to give us a interval. If you've taken college algebra or intermediate algebra or any of those classes similar to this, you're going to see intervals written like this. So this means that we expect our population proportion to fall between 0.201 and 0.249, which means we expect it to fall between about 20% and 25% in this case. So from this, we should be able to work backwards and find things like our point estimate and our margin of error. So we want to be able to go between those two things, between this version and between this version, point estimate plus or minus margin of error. So it's pretty easy to go from point estimate plus or minus margin of error to this interval. You simply take the point estimate minus the margin of error to get 0.201, and you take the point estimate plus the margin of error to get 0.249. So this says determine the point estimate of the population proportion, the margin of error for each confidence interval, and the number of individuals in the sample with the specific characteristic X. Okay. So let's start off with finding the point estimate and the margin of error. So we know that, for example, we know that the point estimate falls exactly in the middle of this confidence interval. So to find the point estimate, in other words, to find p hat, all we need to do is take 0.201 plus 0.249 and divide it by 2. So find the number that's exactly in the middle. Find its average. And so that's 0.225. So there's our point estimate. Then we know these lower bound and upper bound are the margin of error from this number. So to find the margin of error, we can just take our point estimate minus our lower bound. So our margin of error in this case is 0.225 minus 0.201. So our margin of error is 0.024. And then the last thing it asks us for is find x. Well, to find x, we know that p hat equals x over n, right? We defined that in chapter 8. So we can plug in the things we know. We know p is 0.225, and we know x is 1200. So multiply 0.225 times 1200. So x is just going to equal p hat times n, which is 0.225 times 1200, which in this case is 270. Okay, and sometimes these values may have been rounded, so you might have to round off x, because x should always be a whole number, because it's the number of people in the sample that have that characteristic. Okay, so now let's try another one. So once again, to find p hat, we just find the average of our bounds and so for this one, I get my point estimate is 0.862. And then the margin of error is just our point estimate minus our lower bound. Or if you like, you could do the upper bound minus the point estimate. Either one would work. So in this case, that's 0.009. And then last but not least, the number of people with the characteristic is our point estimate times our sample size. So in this case, that's 9250.98, which is 9251. So if you'd like, at this point, you can pause the video for a moment and try these other two examples, and then when you're ready, hit play and we'll go through the answers. Okay, so now that you've given these a try, let's try them together. So once again, p hat is the average of your upper and lower bound. So in this case, you get 0.0625 for the point estimate. And then the margin of error is your point estimate minus your lower bound. So the margin of error here is 0.0115, and then last but not least, x equals your point estimate times your sample size. Which in this case is 70. And then the last one, do the same thing. So p hat equals 0.462 plus 0.509 divided by 2. So 0.4855. Your margin of error is your point estimate minus your lower bound. So 0.0235, and then x is your point estimate times your sample size. So in this case, we get 815.6, so that's 816. Okay, so that's the idea. So that's how these two forms kind of work together, the two different ways to write these answers. So now what we're going to talk about is, well, how to do these things on the calculator. So the nice thing is this is the TI-83, 84 instructions, so we can get rid of those, although it's very easy to do it on a TI-83 or 84 if you wanted to, if you had one at home. The directions are there. You could follow those. But we're going to use the Class Calc app because this is another example where I think it's even easier than the calculator. So in this, in Class Calc, what you want to do is go to Graphing, right, your graphic calculator. Then you're going to choose Stat. Then you're going to choose Tests. And then you're going to do, we're dealing with proportions. We have one variable we're looking at, and we're doing an interval. So we want to pick one prop z int. Okay, so one prop z int. And when you pick one prop z int, you'll notice that it's asking for three things. So when you do that, it'll look like this: one prop z int. And then we're going to put in our x, our n, and our confidence level. Okay, so let's go ahead and look at an example using this. So in a USA Today Gallup poll conducted November 2nd to the 4th, 2007, 768 of 1,024 randomly selected adult Americans age 18 or older stated that a candidate's position on the issues of family values are extremely or very important to them. Obtain a point estimate for the proportion of adult Americans age 18 or older from which the issue of family values is extremely or very important in determining their votes for president. So point estimate, remember, either means the sample proportion or the sample mean. In this case, we're dealing with proportion, so we want to find p hat, which is x over n. So p hat is 768 over 1,024. So 768 divided by 1,024 is 0.75. So there's our point estimate. Then they want us to verify that the requirements for constructing a confidence interval are satisfied. So remember, the way you do that is you need to make sure n times p hat times 1 minus p hat is greater than or equal to 10. So in this case, that's 1,024 times 0.75 times 1 minus 0.75. So 1024 times 0.75 times 0.25, which is 1 minus 0.75, and we get 192, which is indeed greater than or equal to 10, so we can make a confidence interval. So then it wants us to make a 98% confidence interval. So we're going to go to our Class Calc app in the graphing function. Okay, so if you are not in the graphing, remember you just click up in the upper right-hand corner where it says scientific, and make sure you click on the graphing one. Then choose stat, then choose test, so you should be in this menu with test highlighted. And then on my calculator, it's the second one down on the left-hand side, one prop z int. And it should look like this, one prop z interval when you type it. Now notice in the box, it tells you what x, n, and c level are. So x is the number of positive outcomes, n is the sample size, and c is the confidence level. Now, for us, x was 768, n was 1,024, and our confidence level is 98. Now, here's one note. Notice when I try to just put in 98, it yells at me. And that's because I tried to write something that's a percentage in decimal notation without changing it to a decimal. So I have to write 98% as a decimal, which is 0.98. And then notice that it will give us our confidence level. It'll tell us that mu is between 0.7185 21 and 0.781479. So we want to write that as an interval. So our confidence interval would be 0.719, comma 0.781. So we would expect that the percentage of people in the population who who believe that family values are extremely or very important to determining who they're going to vote for in presidential election is between about 72% and 78%. And once again, in the calculator, that looked like this: 1 prop z interval, comma 768, comma 1024, comma 0.98. So it says, is it possible that a proportion of adult Americans aged 18 or older for which the issue of family values is extremely or very important is determining their votes for president is below 65%? Well, we said it must be between 72 and 78%. So is it possible that it's below 65%? Yes, it is possible. Because almost anything is possible. So it is possible that it's below that, but it's not likely. Because 65% is not in our interval. Okay, and so that's the idea. So what I'd like you all to do is go ahead and take a moment, flip over to the next page, and just try doing all the pause the video, try using your calculator to do this problem on page 5, and then when you're done, we'll go ahead and go through it together. Okay, so now that you've had a chance to try this on your own, let's go through it. So first, find your point estimate. So for this case, it's 604 divided by 1,010. Which is 0.598. So about 60% of the population of adults own at least one pet. Or at least of the sample, I'm sorry. About 60% of the sample. Now we need to verify that the conditions are met. So, right, we need n times p hat times 1 minus p hat to be greater than or equal to 10. So that's 1,010 times 0.598 times 1 minus 0.598 has to be greater than or equal to 10. So when I do that, I get 242.8, which is indeed greater than or equal to 10. So we can make our confidence intervals. So then to do a confidence interval, a 95% confidence interval, let's just clear out what we had. Remember, we go to stat, tests, 1 prop z int, and we put in our x, which is 604. Then we hit the arrow over and we put in our n, which is 1,010, and then we put in our confidence level, which is 0.95. So in this case, a 95% confidence interval is 0.568 to 0.628. So 0.568 to 0.628. And once again, that was 1 prop z interval 604, comma 1,010, comma 0.95. And so then if I wanted to do a 99% confidence interval, I would do the same thing, except all I have to change is the confidence level. So instead of 0.95, I put in 0.99. And so on our calculator, that's nice and easy. We can just delete, go inside the parentheses and just delete the 5 from the 95 and make it 98. And when we do that, we get 0.558 to 0.638. So 0.558 to 0.638. And so what is the effect of increasing the level of confidence on the width of the interval? The width also increases, which should make some sense. If I want to be more confident in my confidence interval, I need to make a bigger guess, right? If I want to be very sure that I'm going to make a basket if I'm shooting a ball, one way is to increase the size of the basket. If I make the basket bigger, it's more likely that I'll be successful. Same idea here. The more confident you want to be, the bigger your interval will get. Okay, so we're actually going to skip over this last topic here. It's not something we need to know for this, but I do want to talk about this last problem on page 7. So we're going to skip over page 6 and the first two on page 7 and talk about this last one. So the Gallup organization conducted a poll of 2014 likely voters just prior to the 2004 presidential election. The results of the survey indicated George W. Bush would receive 49% of the popular vote, and John Kerry would receive 47% of the popular vote. The margin of error was reported to be 3%. The Gallup organization reported that the race was too close to call. Use the concept of confidence intervals to explain what this means. So the idea here is behind the confidence intervals is while the sample shows that George W. Bush should win, because it's a sample, we can't be 100% sure. So they calculated confidence intervals. So what percentage of votes should we expect George W. Bush to get? Well, he received 49% with a margin of error of 3%. So that means he should get 49% plus or minus 3%. So that would be an interval of 46% to 52%. Whereas John Kerry got 47% plus or minus 3%, which would be 44% up to 50%. So the reason they had to call it too close to call is because we're confident that it's in these two intervals, but it could be anywhere in these two intervals. It's very possible that George W. Bush would get 46% of the vote and John Kerry would get 50% of the vote, in which case John Kerry would win. So that's another example of how these confidence intervals work in the real world. So that's it for section 9.1. Check back next time for section 9.2.